Okay. Okay. All right. So the claim is we claim that sup of A is equal to D. Okay. So actually, let's do something. Let T naught be the sup of A. And suppose, for the sake of contradiction, that T naught is strictly less than D. Okay. So let X equal to gamma T naught and delta positive such that let's say T naught plus delta is less than D, and B delta X is a geodesic ball. So let me take the closure, which is a disjoint from Q. Okay. So now, as before, you let now let's look at the picture. Sorry. Yeah, so we need the picture. So let's choose a point here, Z. Okay. So let Z belong to the sphere of radius delta around X, such that the distance of Z from Q is equal to the infimum over W in this sphere S delta X, distance WQ. Okay. Then what can we say about, so first of all, by the triangle inequality, the distance from X to Z plus the distance from Z to Q, this is greater than or equal to the distance from X to Q, right? So then distance Z, so X to Z plus distance Z to Q, this is greater than or equal to the distance from X to Q. And this distance, because X, note that A is closed, right? So note T naught belongs to A because A is closed. So this distance from X to Q, this is equal to the distance from P to Q minus T naught, which is D minus T naught. Okay. And this distance from X to Z, this I know is epsilon, is delta. So this implies that the distance from Z to Q is greater than or equal to D minus T naught plus delta. Right? This is because distance xz is equal to delta. Right? Okay. Fine.
Yes, sir.
Now, if beta is any curve from X to Q So in this picture, if I take any curve beta here, which goes from X to Q, this is beta, then there will be a first point of intersection with this sphere, right? A first point where it leaves the ball. So let me call that point W. So then let W equal to first point of intersection of beta with S delta X. Okay, then the length of beta, this is greater than or equal to, so the length of the initial segment from X to W, that is at least delta, plus the length of the segment from Q to from W to Q, that is greater than or equal to the distance from W to Q, right? Yes?
Yes, sir. Yes.
And this is greater than or equal to, by our choice of Z, this is greater than or equal to delta plus the distance from Z to Q, because Z minimizes the distance from points on the sphere to Q, right? So this is greater than or equal to delta plus the distance from Z to Q. Now this is true for any beta from X to Q. So I can take the infimum over beta. So this gives me that the distance from X to Q is greater than or equal to the distance from Z to Q plus delta. So that implies that the distance from Z to Q is less than or equal to the distance from X to Q minus delta. And this, as we've seen before, because X belongs to the set, I mean, T naught belongs to A, this is equal to D minus T naught plus delta. Right? So I get that the distance from Z to Q is greater than or equal to D minus T naught plus delta and less than or equal to D minus T naught plus delta. Therefore, the distance from Z to Q is equal to D minus T naught plus delta. Right?
Yes, sir.
Okay, now now if I let let me call the geodesic from X to Z be alpha in this geodesic ball. Okay. So this part is gamma and this part is alpha. So if I can show that gamma dot alpha, this the joining of these two curves, if I can show that this is a geodesic, then alpha must be part of gamma. And that means that Z must be equal to gamma of T naught plus delta. And that will tell me that T naught plus delta, because the distance is equal to D minus T naught plus delta, that will tell me that T naught plus delta belongs to the set A. And that will give me a contradiction, right? Because T naught was the supremum of A. Is it clear? So I just need to show that this gamma concatenated with alpha is a geodesic, right? So for that, what I will show is that this is length minimizing. So why is that? Let me look at the distance from P to Z, right? So the distance from P to Z is at most the length of this. It's the T naught is less than or equal to T naught plus delta, right? The distance from P to Z. But on the other hand, so now let alpha be the geodesic in B delta X closure from X to Z. Okay. Then distance PZ, this is less than or equal to the length of gamma restricted to the interval 0 T naught concatenated with alpha, which is equal to T naught plus delta, right? On the other hand, also I know that the distance from P to Z plus the distance from Z to Q, this is greater than or equal to the distance from P to Q, which is D. Okay, but that implies that the distance from P to Z is greater than or equal to D minus the distance from Z to Q. And the distance from Z to Q we already proved is D minus T naught plus delta. So this becomes D minus T naught plus delta. So this becomes exactly equal to T naught plus delta, right? But that implies that dpz is less than or equal to T naught plus delta and greater than or equal to T naught plus delta. So dpz is equal to T naught plus delta, which is equal to the length of gamma restricted to 0 T naught dot alpha. So that means gamma dot alpha, this is a shortest length curve from P to Z, right? So by previous theorem, gamma restricted to 0 T naught dot alpha is a geodesic, right? Is this clear? Yes?
Yes, sir.
Yes,
But
sir.
that implies what? That implies that Z is equal to gamma of T naught plus delta, right?
Yeah.
But that and distance of ZQ is equal to D minus T naught plus delta. But that implies that T naught plus delta belongs to A. That's a contradiction. Right?
Yes.
So we're done. So we're done. Is this okay?
Yes.
Yeah. So therefore, sup A is equal to D, and because A is closed, this belongs to A. So that implies that distance of gamma D from Q is equal to D minus D, which is 0. And that implies that gamma D is equal to Q. Okay, so this finishes the proof of A implies E. Okay. Is this clear?
Yes, sir.
Okay, so we've got that if the exponential map at one point is defined on the whole of the tangent space, then I can connect any point in the manifold to the point P by a geodesic, which is length minimizing, right? I can connect any point by a length minimizing geodesic from P to Q. Okay, so I think this is a good place to stop. We'll finish the rest of the proof of the Hoff-Reno theorem on Thursday. So any questions before we finish?
Yes, sir. I just wanted to ask a few questions regarding that connection between geodesic flows and ergodicity. So
Yes, okay, fine. Yes, yes.
So let us first consider, say, we want to look at nice compact manifolds,
Yes.
right, where we can
Right,
make
right.
sense of all
Correct,
this.
correct.
So, like,
Yeah.
one of the most natural things to look at a symmetric space, and then maybe left
Correct,
quotient
correct,
by
correct,
a lattice
correct.
subgroup.
Absolutely, absolutely.
Then we get
Perfect, yes.
hyperbolic manifolds.
Well,
And
if
then
there, oh, wait, be careful. Symmetric space of rank 1, okay, rank 1.
yes,
Right?
yeah, I mean actually, yeah, non-compact symmetric space of rank 1. G
Right,
by
right.
K.
Higher rank is
Then
different.
look at a
Higher
lattice
rank,
subgroup.
yeah,
G and then
actually,
left quotient.
yes, then you'll get a like either real hyperbolic manifold or complex hyperbolic manifold or quaternionic hyperbolic manifold and
Yes.
so on. In these cases, the unit tangent bundle is, like I was saying, it's going to be compact, right? And
Yes.
then if the lattice is co-compact, let's for simplicity, let's take a co-compact lattice, okay? So then that means just a co-compact group of isometries. So the quotient is a compact manifold. Then the unit tangent band, the Liouville measure is a Borel measure on a compact space. It's a radon measure. So the Liouville measure is finite of the unit tangent bundle. Okay. And so you get a finite. So after rescaling, you get a probability measure. All right.
Yes.
And so it turns out for these manifolds, the geodesic flow will be ergodic. Okay. Actually, with respect to this Liouville measure, the geodesic flow will be ergodic with respect to Liouville measure on the unit tangent bundle. Actually, something stronger is true. Once we talk about sectional curvature, you'll see that all these rank one, compact quotients of rank 1 symmetric spaces, these are all of negative sectional curvature, strictly negative sectional curvature. Okay. And that's why I was excluding the higher rank spaces, because the higher rank spaces, they have flats, they have copies of Rn. And so there the sectional curvature in those directions is 0. In other directions,
in that interpretation of rank by the minimum, that embedded geodesic submanifold maximal dimension, something like that.
The maximal abelian subgroup, right? Abelian subgroup. So abelian subgroups will give you copies of Rn. So those will give you flats. Those will give you flats. Okay, so flat copies isometrically embedded inside your manifold. So there the sectional curvature will be 0 because Rn is flat. Okay, so those are non-positively curved. Sectional curvature is less than or equal to 0, but it may be 0 at some points. Okay, so there the behavior becomes a little different. What is nice is when the sectional curvature is strictly negative. Okay, so less than 0, strictly less than 0 everywhere. So then the hyperbolic manifolds and so on are nice, but you can take more general manifolds which are not locally symmetric, just variable negative curvature. Then it's a theorem of Anosov that the geodesic flow on these negatively curved manifolds is, or compact negatively curved manifolds, is ergodic on the unit tangent bundle with respect to Liouville measure. It is ergodic with respect to Liouville measure.
Here again, just here, the Liouville measure would be the Riemannian measure induced from the Sasaki metric, as you are pointing out.
Correct. You can think of it that way. Correct. You can think of it that way.
Okay. So,
you can also think of it by you take the measure coming from the symplectic form on the tangent bundle. That gives you a measure on the tangent bundle, and then that measure you can sort of restrict to the unit tangent bundle. That will also give you it's not exactly a restriction, because the measure of the unit tangent bundle with respect to Liouville measure on the full tangent bundle is 0, right? It's a 0 measure submanifold of the full manifold. But what happens is you have a sort of product decomposition where the tangent bundle is like a product, right? Of
local triviality. Yeah.
No, not local trivialization. I mean, it's how do I say it? It's a union of spheres of radius r, right?
So in that decomposition, yeah.
In that decomposition, right? So in that decomposition, it becomes like a product, and you have the Liouville measure becomes like a product measure with the measure in the r direction, which is just Lebesgue measure on the r direction, and you get a measure on the, well, it's not exactly Lebesgue measure; it's some function times Lebesgue measure in the r direction, but you get a
some
product
weight.
decomposition.
Some weight is involved.
Right. Some weight is there, and then so from that you can extract the component which is on the unit tangent bundle, and that will give you a measure.
Okay. In this way, the geometry influences the ergodic analysis.
Well, actually, for negative curvature, you have lots of ergodic measures, lots and lots of ergodic measures. There's a whole family of measures called Gibbs measures, which come up in something called the thermodynamic formalism. So that's studied in dynamics. The origins come from physics, statistical mechanics. So Gibbs measures are something which they minimize something called the free energy. It's some functional of an invariant measure. And it turns out any Gibbs measure is ergodic. So a Gibbs measure is associated with potential function. Yeah. And
the abundant collection of ergodic
measures. Yes, there are lots of ergodic measures. Yeah.
So just again,
Liouville measure is just one of them. For your symmetric spaces, the Liouville measure is just the Haar measure. Okay, the unit tangent bundle is a homogeneous space of the Lie group, and it's just induced by the Haar measure on the homogeneous space. It's just the Haar. It's just the Haar.
One more question, sir. Like in that sense that. Say if we are having these many measures now, if we talk about, say, we already have an isometric group sitting above, I guess G, like something from G, then like if we ask the question that which of these Gibbs measures or these measures behave nicely with our isometric group also, then I guess that restriction can like give a lesser class of measures maybe.
Well, what happens is actually, so you have, let me draw you a picture actually. I'm just talking. Let me draw you a picture, okay? So we might have time to talk about this later. You need to understand something. So these, this will happen when we talk about cat-1 spaces. So what happens is you have your closed manifold, okay? So here's the simplest example of a negatively curved closed manifold, say a genus 2 hyperbolic surface, okay? So you have the quotient map, and the universal cover is the hyperbolic space, right? Okay. So here okay. So this is, say, X bar, and X is the universal cover. So X is negatively curved. Riemannian manifold. Now what happens is here you have acting here, you have gamma, which is pi1 X bar. This acts on the universal cover by isometries, right?
Yes, sir.
And now this X is what is called a cat-1 space. So it's a negatively curved space, and to such a space, it's contractible. You can associate a boundary at infinity. Like for the hyperbolic space, Hn, the boundary is the unit sphere Sn-1. So here,
which boundary are you talking, sir? Furstenberg boundary?
Well, in some cases, yeah, for rank 1 symmetric spaces, it can be identified with the Furstenberg boundary. For rank 1 symmetric spaces, that's true. For higher rank, something different happens. High rank spaces are cat 0, they're not cat -1. There's some zero curvature, like I was saying. So for a rank 1 symmetric space, the universal it is a cat -1 space, and you have a boundary. It's a geodesic boundary or visual boundary. It's given by taking geodesic rays. A point on the boundary is a collection of geodesic rays which are parallel. They are within bounded distance of each other. So this collection of geodesic rays will define a boundary point. Okay. Now, what happens to the geodesic flow? So you have the geodesics below. Okay. You have these geodesics below which go round and round and do all sorts of things. Above, they lift to bi-infinite geodesics, which are simple without self-intersections. Okay. This will be the lift of this geodesic above. The lift will have a pair of endpoints on the boundary, xi and eta. Okay. And now what happens is, if I fix a point here, a base point, x0, then I can look at the geodesic flow on the universal cover. So any tangent vector, if I take a tangent vector here, v, then it defines for me two things. It defines a forward endpoint. This is v plus, where it flows to in the boundary in positive time. It defines for me a negative endpoint, v minus, where it flows to in the boundary in negative time. And also it defines for me a real number. That is something called the Boseman function. So what I do is I take the positive endpoint, and then I take points converging to this, and I look at the distance from this point to this point on the geodesic, and the distance from the origin to this geodesic. And I look at the difference of these two distances. So if I look at spheres around this point, they will converge to what are called horospheres. So I'll have a horosphere passing through x0, and I'll have a horosphere passing through the foot of this tangent vector. Okay. And this distance here, this sine distance, this is the Boseman function. And so what happens is that this geodesic, if I know the endpoints, v plus and v minus, that tells me that the tangent vector v is on the geodesic joining xi to eta. But then to tell me which point it is on this geodesic, I just need to know this horospherical distance. All right, so three things determine the tangent bundle. So if I look at T1x, then there is a natural map to pairs of points on the boundary. That is a space called del2x cross R. So it's V maps to V plus, V minus, and a Boseman function between the foot point of V and x0 and V plus. So this is a bijection. And what happens is my geodesic flow here, phi t, under this bijection, it gets conjugated to just over here, the geodesic flow acts by translations in the R coordinate. Because flowing by time t will just change this horospherical distance by an amount t, and it won't change the endpoints. So the geodesic flow in these coordinates, this is called the Hopf parametrization. This is the Hopf parametrization. So the geodesic flow just becomes translations. So now if I start with a measure below mu bar, I lift it to an invariant measure mu. Okay, so so mu is a measure on T1x, which is gamma invariant. Okay, so T1x, sorry. I have T1x mu, gamma is acting on this. This is invariant. under this parametrization, this corresponds to, so this is invariant under gamma and under phi t. This is invariant under both gamma and the geodesic flow phi t. What happens is this corresponds to a measure on del 2x cross r. Let me call it mu tilde, which is invariant under gamma and under translations. Okay. In the r coordinate. Now, because it's invariant under translations in the r coordinate, this must be of the form some measure on del 2x cross Lebesgue measure dt on r, because it's invariant under translations. So it becomes a product measure, beta cross dt. So what we get is that beta is a measure on del 2x. So you get a measure on del 2x, pairs of points on the boundary, which is invariant under the group gamma. So this is called a geodesic current. So any invariant measure will give you a gamma invariant measure on the pairs of points on the boundary of the universal cover, this space del 2x. So this is how they interact with the group. So there's no special measure here. There's no one nice measure, but there is one canonical measure, but that uses a notion from dynamics. It's not really to do with the group action. It's more the fact that on the unit tangent bundle, you can talk about what's called the measure theoretic entropy of an invariant measure. That's called the Kolmogorov-Sinai entropy. It's the measure theoretic entropy. And then amongst all measures, invariant probability measures, you can show that there is a unique invariant probability measure which maximizes the measure theoretic entropy. Okay, there is a measure of maximal entropy, and that is a special measure. That is called the Bowen-Margulis measure. So there is one special measure which is called the Bowen-Margulis measure. So Bowen-Margulis measure. So this is on the compact manifold on T1 x bar. This is equal to unique measure of maximal entropy. So this is how you get a special measure on the unit tangent bundle. And this measure for the rank 1 symmetric spaces, for the locally symmetric rank 1 spaces, it is nothing but the Liouville measure, the Haar measure. It is the Bowen-Margulis measure turns out to be just the Haar measure. But for general variable negative curvature, it's some measure which you can't write down explicitly. You can write some formulas, but I mean, there's no other structure really. So yeah. So there is one nice measure. It's the unique measure of maximal entropy. But for that, you have to understand the definition of entropy of an invariant measure. Okay. So you can find that in any book on dynamics, measure theoretic entropy of an invariant measure. So, does this answer your question?
Yeah, actually, the motivation behind my question was that we know about that famous Furstenberg's conjecture, right? On circle, if we look at the continuous probability measure, which is 2x mod 1 and also 3x mod 1, then whether it's Lebesgue measure or not, that famous conjecture. So that's why I just wanted to see whether, like, in more general spaces, how the isometry, because there that is the most obvious isometry, right? Rotation, etc. So here, how does it play out? It is fascinating.
Yeah, actually, well, what happens is you look at the boundary, right? So for H2, the boundary is a circle. What happens is this geodesic current, it has a sort of product decomposition. You can write it as some d nu x. I mean, for many measures, you can construct such as a product measure, d nu x, d nu x of xi, d nu x of eta, divided by some function f of xi eta. F is a positive continuous function. If F satisfies some properties, these nu x's are, these are measured on the boundary, nu x del x. And this measure under the gamma action, this is not invariant. This is what is called quasi-invariant. So with respect to the gamma action, what that means is that gamma star nu x, this is absolutely continuous with respect to nu x. So it's not equal to nu x, but it's absolutely continuous with respect to nu x. Okay, so for example, if you look at Lebesgue measure on the unit sphere Sn minus 1 under the action of the isometry group of Hn, then Lebesgue measure on the sphere is not invariant because the dynamics contracts and expands, you know, so small balls become large balls become small balls. The measure is not preserved, but the measure is quasi-invariant. That is, the push forward of Lebesgue measure will be some function times Lebesgue measure. It will be absolutely continuous with respect to Lebesgue measure. So these quasi-invariant measures are studied a lot in geometry and dynamics. So that is really the picture that one should have in mind, is what one gets is a family of quasi-invariant measures on the boundary. Whenever you have an invariant measure below, or rather you can, there's a relation between families of quasi-invariant measures on the boundary and invariant measures for the geodesic flow. So
Can you, sir, please repeat the last line?
yeah, there's a correspondence between families, this nu x, these families nu x. So what is this measure nu x? I'll give you an example. The nu x would be basically, if x is a point in the inside, you take a set on the boundary, you look at the geodesics joining x to this point on the boundary, you take a sphere, the unit tangent sphere, and you look at the image in the unit tangent sphere here, you take the usual Lebesgue measure of that. So it's the visual measure. This is called the visual measure. So you get a family of measures, nu x. X belongs to the universal cover x. This is a family of quasi-invariant measures. And using these, you can construct a geodesic current by this sort of product formula, which is gamma invariant. And using that, you can construct a measure on the tangent bundle, unit tangent bundle, which is flow invariant. So that's sort of the correspondence. So there's a correspondence between these families of quasi-invariant measures and your flow invariant measures, in particular your Gibbs measures, the flow invariant Gibbs measures on the unit tangent bundle. Okay. So such a correspondence is well studied, yeah. So I mean, just to give you an example, this is this visual measure. In 2 dimensions, it would just be the angle that you see from x. You see, it's just the angle that you see from x. That is the measure. Do you understand?
Yeah, the angle created between the.
Right, the angle of this interval as seen from x. So if you go far away, the measure will become small. The angle will become small. If you go close, the measure will tend to 1. I mean, the angle will become almost pi. So, yeah. So there's this family of measures on the boundary. These are quasi-invariant under the group action.
Okay. And one more question, sir, that
Yes,
in case of, I've seen somewhere vaguely that
let's continue this discussion on Thursday, right?
Next meeting.
Yeah, we have less than a minute. Yeah, so okay, let's continue next time. All right.
Okay, sir.
Okay. All right. So goodbye for today then. I'll see you Thursday.